Hello everyone, welcome to this web series which is on machine learning fundamentals, and we are on to episode 11 today. A very important concept that we are going to discuss today is confusion matrix and other classification performance matrix. I'll be just throwing some, extensive light on what we are going to discuss, and in fact, I'll be opening it up, and then I will be providing you the code as well, Python code in which a program written with the decision tree classifier, and we will be interpreting the results where we will be displaying the confusion matrix and some other very critical parameters which are very important, in fact. And it is essential that before moving forward with other algorithms, other machine learning algorithms that are there, it is very important for us to know the exact interpretation of these values, which will be playing a huge role as far as development of machine learning algorithms is concerned, and at the same time uh, what these parameters, in fact, what kind of insights they're providing us. So before I move forward, one important thing that all the programs which we have done up till now in this series, they are provided on the first episode one video which is there. In the comment back box, you will be getting a link URL which will be a repository, and that repository will be providing you access to all the programs that are there, including the Python programs. So it has been taken into consideration that, instead of viewers writing the programs from the scratch, we'll be providing, in fact, programs so that they can copy it from there, or they can copy the programs and they can run those programs in their environment. So that will be saving a lot of time as well. So coming back to the topic of discussion, which is there for this particular episode, we are on episode 11, confusion matrix and classification performance. So this is a foundation model, evaluation model. So academic exploration of fundamental classification evaluation techniques, precision recall dynamics, and strategic matrix selection for robust model assessment. So this is what we are going to learn, and this is the kind of benefit it is going to provide us. So let us start. Understanding model performance evaluation. Fundamentals, which are their confusion matrix structure and interpretation. We should be able to first of all understand what confusion matrix is, and then interpret all it in an appropriate manner, and understand various aspects that are related to it. So that's number one. And then mathematical understanding also has to be there. For example, understanding what is precision, what is recall, and F1 score formulas which are there, and what F1 is. So we'll be understanding that as well in this particular episode. And the practical applications, definitely it will be we'll be applying to real classification problems. Simple accuracy matrix, we can move beyond that, because there are insights as well. With these parameters, we'll be getting insights, and it will be giving us insights about how a particular machine learning model is performing beyond what is visible. So for that particular thing, to understand that, sorry, it is important that we'll be understanding these parameters. What is confusion matrix? A foundation of classification evaluation. So if we go to the definition of confusion matrix, it's a tabular representation comparing predicted versus actual labels. That means, sorry, the confusion matrix will be able to give you that, how the model has done the prediction, and what were the actual labels or the values which were there, and how a model has performed, and comparing those with those values that have been predicted by the model. It goes beyond single accuracy matrix. So confusion matrix is giving you much deeper, a holistic, a deeper view of a deeper view of how a particular machine learning model has performed compared to single accuracy. So it's not just a simple or single accuracy matrix which is there. It's a comprehensive view of model predictions and revealing error patterns that are there in the model, and it also identifies systematic biases that might be there in a particular machine learning model. So it is giving a comprehensive understanding of how a particular machine learning model has performed and what are the shortcomings, and if there are any, where exactly are those shortcomings, and what is happening in there. So that is something which is very detailed. It is giving a holistic, comprehensive view of comprehensive view of these things. So matrix structure. So this is rows. So for example, we'll be taking an example of a matrix and how we have to in fact interpret that. So rows are actual values and columns are predicted values. So we are going to understand it in a deeper manner. Diagonal values are correct. Diagonal values are those which are like this, in this manner. So we say diagonal. So that will be starting from left, top most left cell towards the bottom right cell. That is a diagonal like this. And off diagonal, which is going like this, they are the errors. So we are going to understand that. If you just see this particular figure which is coming now, uh, you see the confusion matrix which consists of these two rows, and there are two columns, and we start with the topmost left cell which is there, or you can say a left first value in the in row first, left first row, left cell in the row 1, that is showing 5, and then we are having on the right hand side 1, and then bottom left is showing 1, and then there is 3 with the green. So what are these how these values we can just how they are interpreted? I will be just giving a complete comprehensive interpretation of this. So first of all, you have to understand the first when it goes to diagonal like this, those are the true values. So there were, what does that mean? There were 5 students actually who were predicted pass, and they have passed. That's what first left side of the row 1 is saying. That is the first cell or first value of row 1, which is in yellow. So there are 5 students who passed, who were passing, and they were predicted as pass by the model. On the right hand side, it is showing a false value. There was one student, actually, one student was there. So these actually one thing is there. I'll just get it right. I want to take it in a sequence. 5 students, one student, 3 students. So what is the sequence? I will just first of all let me just make you understand what these terms are. So true positive. It is little I think. I'm just doing it a little prematurely, explaining these here. It should be done after these terms are explained. True positive TP, true negative TN, false positive FP, and false negative FN. So we have to give in fact a distinction between them and what kind of impact these are having. So if you just see this particular slide now, so I had actually taken this slide a little earlier. So what each value means: 5 top left true positive, students passed and model said pass. So if you see here, coming back, it's the 5 students who were actually passing and model said that they'll pass. So they have been rightly, correctly predicted. Then we can say top right, that means the second value which is there, false negative. So student passed but model said failed. Actually one student was passing but model predicted that student has failed. That's called as a false negative. It is not true negative, it's false negative. False negative is mistake has happened. It was a pass actually, but a model has predicted it as fail. Now we are having bottom left, which is false positive. One is, a false negative, one is false positive. False positive is what? Student failed. Student has actually failed, but model has said student has passed. So model predicted that student has passed. That is the value which you can find on this matrix on the row 2, bottom row, left hand side, bottom left. So student is here predicted as pass, but actually the student has failed. So this is this particular thing is called as false positive. And then we are having bottom right, which is true negative. So true negative is that students failed and model said that they failed. So model has rightly, correctly predicted these students who were failing, and model also predicted them as fail. So these are actually the interpretations. That's what we said, that the diagonal like this, when you're having diagonal like this, so it will be the correct values, and like this we are having off diagonal values, which are in fact the incorrect or the mistakes that model has done. Sorry. The critical importance of confusion matrix analysis. So accuracy limitations, masks, error, distribution and types, what matrix reveals, where and how errors occur. You're having class specific insights, performance patterns by category, real world examples. So definitely they are, in fact, confusion matrix is playing an important role, in providing that big picture, in fact, a holistic picture of how a particular model is performing, rather than limited things. We are moving on to one more very important aspect, which is called as precision. We are measuring prediction quality. That's what precision is. So if we see the formula of precision, precision is equivalent to true positives divided by true positives plus false positives. So true positives divided by true positives plus false positives is what is precision. So if the precision is equivalent to 1, that means you are having the highest precision quality. That means it is 100% result. And as it is decreasing, the accuracy, the precision is decreasing. Of all predicted positives, how many are actually correct? Example, TP is equal to 5. True positives is equivalent to 5. In the previous example, if you just see, true positives are 5, and true negatives are, if you just see, true positives plus false positives, sorry. So true positives plus false positives. So if you just see here false positives, how many are false positives? So that is 1. So 5 plus 1 is 6. And if you just see, true positive is 5 divided by 5 plus 1, that is 6. 5 by 6 will be the average, and it comes roughly around 83.3%. So that is what precision will be. So it depends. It will be, as it goes on increasing, as it is near to the precision value will be, nearing to, 1. So it is going to be 100%. So high precision means low false positives. So definitely. So false positives will be less, and true positives will be more, then your precision will be high. Conservative positive prediction. So definitely this is little conservative as this goes, but it is a positive prediction which can tell us the scale of precision a particular model is having. Precision is very important in some of the applications, medical diagnosis, fraud detection systems, because there we'll come to know that to what precision a particular machine learning model will be operating, where these things can be very critical. It can be criminal justice predictions and precision recall trade-off. These are the areas where this can be implemented. Common pattern: cost of false positives exceeds cost of false negatives in these domains. Why false positives exceed the cost of false negatives? So false positives will be telling us what? The cost of false positives exceeds the cost of false negatives. So false positives in these domains where we are having higher precision often reduces the recall. Okay, higher precision will be reducing the recall, but in these areas, false positives. So what are false positives? If you just see again here, the false positives are that somebody is fail, but model is saying it is pass. So if you correlate it, what false positive is, you will just understand that there is a fraud which is detected as normal. There is a problem, medical diagnosis. A problem is there in a patient, but it is saying it is clean. Spam email is there, but it is saying that this is a normal email. And in a criminal justice prediction, it will be predicting an innocent that it is or for example, a culprit will be there, a criminal will be there who will be given as that he's a he's innocent, and precision. So in these cases, if you just see these areas, it's very critical. This is very critical. So the cost of these false positives is exceeding the false negatives, which will be other way around. That is other way around will be some false negative means it will be detecting something as fraud, which is not a fraud, which is a normal case. But if you say false positive, that will be that is that's going to be if you say a false positive is going to be very critical in these circumstances. Recall is measuring coverage and sensitivity. What is the recall? And what is form line interpretation? A recall is true positive divided by true positive plus false negative. So if you just see recall, we can just see here precision true positive divided by true positive plus true positive plus false positive. Here it is true positive plus false negative. So that is the recall. So the difference between this is, in case of precision, we'll be having true positive divided by true positive plus true negative, and then false positive, sorry, so true positive plus false positive. But here recall is true positive divided by true positive plus false negative. So that is the difference. Of all actual positives, how many did the model correctly identify, and also as sensitivity or true positive rate? So example will be again in the same case. We can just say the recall, if we have to calculate, it will be again 83.3%. Actually, in this case, recall and precision will be all same. And we can just say, if for example, recall and precision value is same, your recall and this precision value is same, you can just say that if you just see here, recall and precision is same, so you will say the F1 score is same. That we haven't moved to that particular extent now, but I'm just saying that F1 score will be same. So we'll be going to that as well and understand. High recall means low false negatives and comprehensive detection of positive cases. So that is something here. So recall, precision, and confusion matrix we have taken. And applications where recall will be critical. It will be disease screening, cybersecurity, threat detection, quality control systems. High recall prioritizes comprehensive detection where false negatives carry severe consequences. Uh, False negative means something is predicted as negative, but in a false manner, but it is actually positive. So missing a threat is worse than false alarm. So definitely missing a threat will be very critical. Cybersecurity, threat detection, quality control. So that is, these are the applications where it is. And then F1 score, the harmonic mean, balancing precision and recall. F1 is equivalent to 2 into precision into recall divided by precision plus recall. So in the cases where we have seen that precision and recall are same, you will see that F1 score is almost similar as well. You'll be getting the similar values for F1 score as well. So where F1 score is selection analogy, precision of selected students, how many deserved the scholarship, recall of all deserving students, how many were selected, just giving an analogy kind of a thing, where it can be, they can be correlated. F1 score, how balanced and fair is the selection process? And we have to minimize the F1, maximize balanced F1 score. So definitely you have to maximize the balanced F1 score which is there. And there are key takeaways. Confusion matrix provides the complete performance picture. No single metric tells that whole history. Definitely, there is no universally best metric. Selection depends upon the domain, context, and error cost that is there. Definitely, the precision recall trade-off is fundamental to classification. Understanding your errors is more valuable than celebrating the accuracy. That is something, because otherwise, if you're not getting these values and interpreting them in a proper manner, you might be superficially weighing or evaluating a particular machine learning algorithm, which actually will not be performing to such an extent as it will be visible. So this is, what is there for this session. But here I would not stop here. I would like to just show you the program which is there for this machine learning program for this, which is putting this confusion matrix, outputting that. So let me just open the file. I'm having a program already written there, and these programs, as I told you, they will be available on uh, this uh, repository which has been provided in the link which is there. I will be just going to this one which will be showing us the confusion matrix.